How's it going, my friends? Today we're going to talk quickly about what's going on today and what we're getting ready for tomorrow. So today I want to talk a few minutes about just friction and some of the friction calculations we've been doing. Today you're going to practice some of those calculations. Tomorrow we have another lab that involves the acceleration of objects based on their forces and masses. And then Wednesday and Thursday we have our bouncy spring lab where we're going to hook up to some huge springs and fling ourselves into the air. So that'll be fun, but that means we have to stay on task, which means we've got to get through today's stuff today. In the past, some of you have taken a day when there was a substitute as a sign to ease up, relax, chill out, and not get your stuff done. And if that happens, then we'll have to burn another day in class, which means we'll be off and won't be able to do the spring stuff on Wednesday and Thursday. And if we don't get it done this week, we're not doing it. It just won't fit next week. So we've got to do it Wednesday and Thursday to have it make sense in the sequence. So long message short, make sure you're getting on task, you're working hard, you're getting your stuff done today. All right. So in this video, I just want to very quickly run you through some of the general ideas of what we've been working with and make sure you're familiar with those equations and how to apply them. All right, to start with, let's write down some of the equations. So first of all, we have our acceleration equation. And that is acceleration is equal to the net force divided by the mass. So whenever you know the net force acting on something, how hard something is being pushed, the mass of the object you can find as acceleration. And in fact, if you know the acceleration and net force, you can find the mass, and mass and acceleration, you can find net force. So you can use as any combination of two. The next one we talk about is the weight of an object. F sub g, also force of gravity known as the weight of the object, is equal to the mass of the object times g. And this number is the acceleration due to gravity, which is that 9.81 meters per second number. And of course on worksheets, we can do the approximation of 10 meters per second because we're a little bit lazy. So those two equations are up first. The one we just learned recently is this one. So the force of friction is equal to mu, the coefficient of friction, times the normal force. And this is the force pushing down. Now, for an object sitting on a table, oof, that was a terrible table. Hang on, let me back that up. For an object, it's not much better, it's good enough. For an object sitting on a table, like this wonderful table, we have this object. It's being pulled down by the force of gravity, and it's being pushed up equally by the force of the table. In this case, these two forces are equal, and this force of the table is the normal force, okay? Which happens to be equal to the weight of the object. So far we've been using that here. We also said, I don't know if I talked to all groups about it, but that the weight isn't really what we're talking about. It really is the force that's pushing objects together that causes the friction. So for example, my hands weigh the same, and if I put them together and rub them, I get a very small amount of friction. But if I push them together really hard, I get way more friction. It gets harder to rub them together. Right? So I get this large amount of friction. And it's not because my hands weigh more, obviously, it's because they're being pushed harder together. This F normal is the force of the objects being pushed together. So let's write that up here. So this is the force pushing the objects together. And it's called a normal force because in math the word normal means 90 degrees. So that's that one. So on a ramp, it looks a little different. So here's my wonderful ramp. I have an object on there. It has a force of gravity, F sub g. And of course we think of that force of gravity as pulling in two directions. And I'm going to draw the components as blue. One of those forces pulls down the ramp. You can see I left it 90 degrees or so. And we've been calling that F sub g in the X. And the other component of force pulls directly into the ramp, F sub g in the Y. And these two blue forces add together make this central force here, right? Now the question is, which one's this? So this should be this force normal is the force pushing the objects together, grinding them into each other, which is F sub g in the Y. So that would just be that force. So this force that pushes the object into the ramp is the F sub gy that goes here. And this mu, this coefficient of friction, is a constant. You have to either do a bunch of measurements like we did in the lab ourselves to calculate for this for every different surface, or you have to look in a table and look them up. There's been a lot of work done to calculate these, and there's tons of them out there already done for us. So that's that. That's our friction equation. Now the next thing I want to talk about are how to calculate F sub gy and F sub gx, and we've done this before. I'm just going to remind you. Remember that the other equations we have is that F sub g in the x, and this is going down parallel to the ramp, is equal to the overall weight, so the total weight of the object, times the sine of theta, where theta is the ramp angle. And that would be this angle here that you measure here. That would be theta, whatever that is. And then F sub g in the y is equal to F sub g, the total weight, and the cosine of theta. And again, that is the ramp angle. So that gives you how much of the weight is in the x direction, how much of the weight is in the y direction. And these two numbers here, this sine theta and cosine theta, tell you the percent of the weight that is in either the x direction in the case of sine, or in the y direction in the case of cosine. So that's pretty actually fantastically cool that this weird number that spits out like 0.375, that tells you that 37.5% of the total weight is in the y direction. Right? All right, so that's it. Those are the equations you need for today. It's just a matter of figuring out how to apply those equations. I'm not sure why I'm drawing a red box around this, but I am. So F sub gx, F sub gy, weight of the object here, accelerations here, amount of friction you can figure out from here. All right, so you guys are doing a great job. Work hard today. Get yourself squared away. If you need this video, you can check it out on YouTube. Just go to, search for Joshua Haza, and I'm sure you'll figure it all out from there. All right, best luck.